Hello, everybody. I'm doing Yu Liu. Thanks for the invitation. I'm really glad to present our work at our Dynamic Rupture workshop. My collaborators are Doctors Benchun Duan, Catherine Shara, and Doug Yu. My topic is earthquake cycle simulations, paleoseismic record, for geometric complexity, and stress heterogeneity. The work is funded by SCAC and NSF. I will first talk about the motivation of the study and the method and model, some results, and a summary. In assessing seismic hazard for a given fault system, we care about three questions. What could the size of the next big earthquake be? When would it hit? Where might it start and propagate? Paleoseismic data provide us valuable information regarding the timing and sizes of past earthquakes. For strike-slip faults, the coefficient of variation, the COV of recurrence interval, is about 0.4 to 0.8. It indicates quasi-periodic behavior of the fault system. At Fraser Mountain and Redwood on the Sandris fault, COVs are about 0.7. So if you have a lot of timing from dozens of sites in a given fault system, you can get the maximum rupture model, and then that can tell you the rupture extent. Sharon and Yu did a really comprehensive summary of the paleoseismic data on Sandris and the San Jacinto Fault, and it really shows complex rupture segmentation. So the figure on the right are from Sharon and Yu 2020, and the top panel shows the fault geometry of the Southern San Andreas Fault and San Jacinto Fault. And there are two big fault geometric complexity: the Big Bend, a prominent restraining band, and the Cajon Pass is a step over and a triple junction between the two faults. And the panel at the bottom shows quite diverse rupture scenarios, like historic event, 1857 rupture, the Fault-Tahun earthquake, 1812 Redwood earthquake, and some small ruptures on the San Jacinto Fault. There are several types of ruptures like this one. The rupture is stopped sort of by the Big Bend. And there are some 1812-like ruptures, 1857-like ruptures. And also there is a possibility that a big rupture can break the Southern San Andreas and also the San Jacinto Fault simultaneously, like this arrow shows, like 33 and even these later events. So the question is, what mechanical factors lead to the complex rupture segmentation? And it seems fault geometry plays an important role here. And to understand it, it will give us better understanding of the rupture dynamics in the fault system. We use a multi-cycle dynamic model to simulate the process. The method includes two parts. The coseismic dynamic ruptures are simulated by EQDyna, a finite element software. The interseismic stress evolution is simulated by 1D analytic viscoelastic solution. In terms of the friction law, we use the slip and weakening friction law proposed by Duan 2019. And it's a combination of a slip weakening law and with some frictions rate dependency during dynamic ruptures. We have two important inputs in the model. One is the fault geometry, another one is the loading. So the figure here shows the fault geometry obtained from the community fault model 5.2 for the Southern San Andreas Fault and the San Jacinto Fault. So there are two important angles. One is the theta, and that's the strike angle relative to the left end of the fault. Another angle is alpha, So the arrows here shows the maximum shear strain rate and which are rate direction, which are derived from a geodetic model by Smith-Conner and Sandwell 2009. And the alpha is the angle from the strain rate direction relative to the strike of the left end of the fault. So the figure on the right shows the inputs. The top panel shows the maximum shear strain rate, and you can see it's really high on the carousel plane, and it goes down towards the San Bernardino segment. And the theta angle, you can see near the Big Bang, we have a really large band angle over 40 degrees. So based on empirical relations for restraining band with band angle over 40 degrees, typically rupture will not pass it. So it will stop most of the ruptures. But from paleoseismic record, you can see rupture can get over Big Bang, not that hard. So the reason is here, theta minus alpha. This is what I call it effective fault geometry, and you can see near the Big Bang, this subtraction gives you about a 20-degree band angle. So yeah, for a 20-degree restraining band, ruptures can pass the band more easily. After we run thousands of earthquakes in a model, we first want to validate the long-term slip rate. The figure on the right, the solid line shows the numerical slip rate, and the dashed line shows the user-free geologic slip rates. And you can see these two values match well. And you may notice there's a dip in our numerical results near the Big Bang. And that's typical for a restraining band. And this figure shows the slip distributions for earthquake sequence over 6,000 years. And you can see there are quite diverse rupture scenarios happening in the system. And the important question is whether our model can produce the rupture scenarios reviewed by Paleoseismic record. And we have several, this figure shows the representative and the special events in our model. And rupture A shows a rupture that breaks all the simulated fault system, including the San Andreas and the San Jacinto fault. And the dashed line here shows the rupture time curve. So the rupture starts somewhere here, and it propagates to the south. Rupture B, it is stopped by the Big Bang. And rupture C, it just break the Claremont strand of the San Jacinto fault. And importantly, our model can produce the 1857 fault-Terhune-like ruptures, like rupture D and rupture E. You can see the slip amount is about 5 meters north of the Big Bang, and the value gradually taper down towards the Terhune Pass. And the rupture initiate north of the Big Bang and propagate to the south. All these dynamics match well with previous studies. And also we have the Redwood earthquake. You can see it breaks mainly the Mojave segment and a small part of the Claremont strand of the San Jacinto fault. And this part is overlapped. It's overlapping with the tail of the 1857 ruptures. We also have these small ruptures that break just a part of the Big Bang. If you recall the Paleoseismic record, there is also a similar one. And also this one, 1980 earthquake. And we compare them with the Paleoseismic record. And it seems our model can produce quite a lot of the scenarios from the maximum rupture model. And this panel shows the stress the shear strength before rupture D is quite heterogeneous. Important question is how the stress looks like over earthquake cycles, and our results demonstrate the shear stress or strength heterogeneity is strongly related to fault geometry. This figure is from our another study. So we applied multi-cycle dynamic models to another earthquake gate, the Pingdingshan earthquake gate along the Untitled Fault in northwest China. So it was published on Tectonal Physics this summer. So the bottom panel shows the fault geometry, and you can see we have a regional restraining band and a regional releasing band, the light blue color. And here the strike variation shows it more clearly, and these are positive values and negative values. And the top panel shows the shear strength before several big ruptures. And you can see we have really high strength near the restraining bands and really low strength near the releasing band. But inside of this regional restraining band, we also have a strength trough, and this is actually related to this local releasing band inside of the regional restraining bands. So to conclude, releasing bands lead to strength troughs, and the restraining bands leads to strength peaks. Important question is how to justify the stresses. We have cohort measurements and or focal mechanisms, but they are typically scattered data points. An alternative way is by putting dynamic ruptures in the context of earthquake cycles. In that case, the stress states will evolve in a physically self-consistent way. In this case, stress is actually not considered explicitly. So the credibility of the model is actually from, we can feed our model to as many types of data sets as possible. So there are many data sets we want to include in our models. And in this study, we try to emphasize the Paleo earthquake records. And at the same time, we also have geologic slip rate, fault geometry, friction laws, and geodetic constraints. But definitely we want to have other type of observations, models, or data sets in our model. In that case, we can say, the stress from the model is reasonable. So where might the next big earthquake start and propagate? Our model demonstrates in this fault system, large ruptures tend to initiate north of the Big Bang and propagate southwards, like the 1857 Fort Tehun earthquake. This information may be important to the ground motion evaluation in this region because of the low velocity basin structures there. Like also in 2008, the Terra Shake 2 exercise shows ruptures from the different directions may have different shaking maps in the Los Angeles region. So to summarize, stress heterogeneity from interactions between fault geometry and dynamic ruptures produce complex rupture extension and recurrence, which are similar to the maximum rupture model from Paleoseismic record. And large ruptures tend to initiate north of the Big Bang and propagate southwards in this fault system, similar to the 1857 Fort Tehun earthquake. Okay, thank you for your attention. And our manuscript is submitted to JGR. It is now under review. I'd be happy to take any questions. Thank you.